Hello, my name is Bob D. Hilster, and I am your particle model guru. Today we're going to talk about, or try to answer question number 2. These are questions that people come up with. They hear about things in science, and they watch movies and see things happen, and they question, like the first question, why aren't there flying cars? Today I'm going to ask the question, why can't I walk through walls? Well, here's a picture I got off the internet which shows Harry, although this is not really Harry. This is a guest at some place, I don't know where this is, who walks up to this wall. The cart is stuck against the wall, making it look like the cart's gone halfway through the wall, and you stand there and hold on, and it looks like you're about to walk right through that wall. And we asked the question, why can't I walk through walls? Well, one of the reasons we ask that question is because we hear from science that the atom is mostly space. And all that stems from a gentleman in the 1800s, Ernest Rutherford, who did this experiment. He took a source of he caused alpha particles to be emitted, and he shot them right through a thin gold leaf, and he expected them to go straight through. And he surrounded these events with a detecting screen so he could see where the alpha particle hit. And as you can see, most of the particles go straight through this golden red line. Most of them are going through, but obviously what he detected was that there's some other places that they were hit. Not so many, but they were there. Now, the alpha particle is actually defined as 2 protons and 2 neutrons, which makes it look like a nucleus. In fact, it would be the nucleus of a helium-4 atom. So that's what they're shooting at this. Now, all the way through my description of the particle model, I've been saying the same types of interactions happen all the time. A particle like the G1 or the G2 will pass through an object, will hit and scatter, and be trapped. This happened in the 1800s, and they knew about the fact that the particle could go through atoms and it would scatter off of them. It's been known for a long time. And so Ernest Rutherford expected there on the left here that there were, apparently he expected just electrons in the atom, and that the alpha particle would fly basically through all the time. But this is what he actually got, and based on that, he assumed that there had to be this larger object inside the atom that caused a lot of the deflection. And so this is part of how we evolved our model of the atom, and the fact that we know there's open space. So there is lots of open space, and here's some statistics about them. The nucleus of an atom is extremely dense and contains nearly all of the mass of each atom. And well, I can argue the point about mass is an assignment. Mass is not contained in an atom, but mass is a assigned property that helps us describe the motion of the particle when it hits and moves. But they go on to say electrons contribute very little mass to the atom. In fact, it takes 1,836 electrons to equal the size of 1 proton. And in general, it's been estimated that of the space allocated to the atom, 99.9% of that space is empty. That's the volumetric space. I assume the cross-sectional space is probably going to be less than that, but nonetheless there's space. One way to look at it is if the atom was the size of a sports arena, the nucleus would be the size of a pea sitting right there in the middle of that sports arena. Lots of space, the particles are very small. If there's so much space, why can't I push my pencil through my calculator? Well, I have my calculator here, and this is my pencil, and I'm going to try to push it through. Not only do I not get through, but you can hear a click where it makes a sound, a noise, when it tries to go through. Well, the standard model, or the what science says today, if you look it up, the reason you can't push the pencil through, or why you can't walk through walls like Harry, is because of the Pauli exclusion principle, or because of electron repulsion. Particle model has its answer. It has to do with G1 interaction and G2 gravity. Well, let's look at the Pauli exclusion principle. This is taken from Wikipedia. The Pauli exclusion principle is the quantum mechanical principle which states that two or more identical fermions, particles with a half-energy sphere, cannot occupy the same quantum state within a quantum system simultaneously. Well, I'm not an expert in quantum mechanics, but obviously they're making a what I typically see as a reverse statement. The reason they can't occupy the same state, same place, is because of the principle. We write down the principle, and the particles have to come over, read the principles, and that way they know how to behave because they've read our principle. Our principle doesn't control them. Anything we describe, we're trying to describe what's happening in some way, but it's not the cause. But the quantum state is defined by quantum mechanics using four quantum numbers. There's the principal quantum number, n, which seems to be related to the number of protons and neutrons in the atom or the particle, whatever it is. The angular momentum of the particle, the magnetic quantum number is the magnetic. Both the angular momentum and magnetic number generally, to me, are related to the spin, but yet it still has a spin quantum number. These are four numbers that they use to define the state. And this all gets related to an equation developed, and you can assign values to these, or numbers to these four states, and when the two particles have the same values, the state collapses, the value is zero, and therefore that state is excluded, and hence Pauli's exclusion principle. It's all mathematics. It's a very complicated answer to a very simple problem. Of course, electronic repulsion, I don't really need to explain that. Two electrons coming at each other are going to repel. That's because that's what they say charged particles do when they have the same charge. Whether it's positive charge or negative charge, they're going to repel each other. And so when I push my pencil against the calculator, the electrons in the pencil are being pushed back by the electrons in the calculator, and you can't get through. Not unreasonable answer, as long as you agree with charge. The particle model has no exclusion principle, except that no two particles, because they're physical things, can occupy the same space. It can't get any more simple than that. I don't need a principle in the sense to say that. Electron repulsion, the particle model does not have negative or positive charge that causes repulsion. However, moving particles will push back on each other when they hit. So there is an equivalent to electron repulsion in the particle model. And so these are the two that help explain why we can't walk through walls or push the pencil through the calculator. First of all, there's free G1s that are flying through space. When they hit, they will scatter. There's an interaction there, and they can't go through each other. Particles don't go through each other. Smaller particles can go through larger particles if there's space available. G1 particles, when they hit, will generally stay in orbit. So the G1 orbitals in the pencil and the G1 orbitals in the calculator will hit each other and will push back, but they generally stay in orbit. But not always. It may depend on the material. You take a rubber balloon, rub it against the wall, you can move G1 orbitals from the wall to the balloon. So they don't generally stay in orbit, but they can move in that case from one orbit to another orbit. But so the G1 hitting each other are going to keep you from pushing the pencil through the calculator. But one of the main forces, G2 gravity. G2 gravity holds the nucleus together, the atom together, and the molecules together. That's one of the functions of G2 gravity. So the question is, how much force does it take to push the atoms apart? Because if you're going to push the pencil through the calculator, you've got to move the atoms apart to make room for them. Now, in 2008, I was at the Trinity site in New Mexico, and there they were able to push atoms apart. Took a lot of force to do that. That kind of force is needed, and you need a special material to do it. Can happen. Well, it's not going to happen with me pushing my pencil and trying to push it through the calculator. I don't have that much force. So in terms of pushing the atoms apart, what you're trying to do is take an atom in the pencil and push it in between and cause these two atoms to separate so that this particle can go through and this atom can go through and that atom can go through. But you gotta overcome G2 gravity, which is extremely strong. So because of the G1 interaction, because of G2 gravity, we're not going to walk through walls like Harry, and we're not going to push our pencil through the calculator. And I'm very grateful, because if that could happen, I wouldn't be sitting in my chair. I'd be falling through my chair and through the earth. So yeah, I'm grateful we can't walk through walls. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.